Well, it's a great pleasure to be here. It's the third time I've been to Frascati, and I've been to Italy many, many times. And I wanted to just start, before I start my talk, I just wanted to give you a little sense of where I come from. We come from Western Australia, and which has been in the news lately because because Perth has been the centre of the search for the lost aircraft, the MH370. But some years ago, we set up this centre called the Australian International Gravitational Research Centre, which is in a place in the empty land about 80 kilometres from Perth, and it is a site where we want to build a gravitational wave detector like the Virgo detector at Kashina, which is a wonderful piece of technology that I've just been visiting. And in this picture, there's one thing which is not real, and that is our dream, which is to build this big, big detector. That is not real. But everything else here is real, and I want to show you the connection with Italy. Because in our collaborations with Italy, I had been to Pisa many times, and we had a plan that while we built a research centre, which is this part, we would also build an education centre. And this is the education centre. And we were inspired by our colleagues in Pisa, and we decided that anywhere where you do gravitational research, you must have a leaning tower. And so we built a tower which is called the Leaning Tower of Gingin. And this is used to inspire young people with the story of Galileo. They go to this tower. At the bottom of the tower, there is a water tap, and you can take a balloon and fill it with water, carry it to the top of the tower, and then drop the balloon. And at the bottom there is a sandy area, and you make beautiful craters. And next door we have an astronomy centre, and then you can go and look at the craters on the moon and see that they look just like the crater that you made with the tower. But we also have a large gallery where we try to teach Einsteinian physics, which is really the topic of my talk today. And because this is modelled on the Piazza de' Miracoli in Pisa, of course we had to have a baptistry as well. And this is the baptistry. This is the largest buckyball in the world. And it is on top of tall walls, so it is a 20-metre dome. And there we have exhibition about the history of the universe. So if ever you come to Perth, please come and see this centre. 20,000 people a year come to the centre, and mainly students. And I think you will enjoy it. Oh, what is happening here? But now, just to finish giving you a context, I'm just going to escape from this for a second and come to... I've lost my glasses. I want to I have a little bit of video I'd like to play you, which gives you a little bit more of a sense of this place. It is in a big empty plain.
1 hour's drive north of central Perth, an extraordinary complex of facilities is located in the middle of a large tract of pristine Banksia woodland. The Gingin Gravity Precinct was set as part of a nationwide collaboration to support Australia's participation in the international search for Einstein's elusive gravitational waves that travel through space at the speed of light. Researchers hope to use these waves to make direct observations of black holes and the birth of the universe.
So, I'm not going to play any more of that because it is taking time from my presentation today. But so, to start my talk, I want to talk to you about the research that we've been doing to try to change the paradigm by which we teach science to young people. And we call this Einstein First. We don't teach Euclidean geometry first, we teach them first the geometry of curved space. This is a collaboration between a whole lot of people, and it's called the Science Education Enrichment Project. We have several PhD students working in this area, and I'll try to give you a sense of what we've done and how well it works and how it is something that is really possible to do. But I want to first give some introduction to it. I called it Teaching Physics in the LIGO-Virgo era because this is the era in which we are going to be observing curved space. Already astronomers observe curved space regularly. It's the era of gravitational wave detection, and it's the era when Newtonian physics is going to be really obsolete as a fundamental way of understanding the universe. Here, of course, is the Virgo detector in Kashina. We were there last week, and we actually climbed to the top of one of these mountains here to look down over this beautiful, huge instrument across the plain. So, what I want to talk about is first of all, the 25 centuries of discovery about space, time, matter, and radiation. And I want to go on to talk about why it's important that we should be teaching our youngest children our best understanding of the universe and not some obsolete fiction. I'm going to show you some trial results from children aged 11 and upwards, up to teachers, to show that this is something which is possible. I'm going to talk about why people think it is impossible. And I want to show you how we can make it fun and interesting. And I have a few little videos to show you that the deep concepts can be taught in a very simple, easy way. Any teacher can do it. So we call this all Einsteinian physics, mainly because we need to have a nice label to explain what we are doing. And by Einsteinian physics, we mean curved space, warp time, the idea of photons, and the idea of quantum uncertainty. So all these are ideas that we want to be teaching to very young people. Let's start with the history, which goes back to Euclid. Of course, it goes far beyond Euclid. The history goes another 1,500 years beyond Euclid, when geometry was starting to be understood. But Euclid's book is interesting because it is the book that has been used to teach science for the last 2,000 or more years. It's the most influential science book of all time. It has been published in 1,000 editions, and it's taught in every school. It's either taught, I was taught by the actual book elements, and I'm sure there are some people in this room who studied from that book, but I know that the modern textbooks have taken the content of it and put it into other books. So that is the first that people learn about geometry. But people have been trying to understand the geometry of space. I think the quest to understand the idea of space has been a part of our culture for thousands of years. And one of the approaches to it relates to the number pi, which of course is the ratio between the circumference and the diameter of a circle. Calculating pi uses Euclid's geometry. One of the traditional way of estimating the value of pi is to draw a polygon inside and a polygon outside a circle, and the value of pi is determined by the circumference, the difference between these two circumferences. This was a method that was developed thousands of years ago, but the geometry is a geometry of flat space like paper, and all calculations of pi assume that space is flat. The digits in pi represent a theoretical precision of flatness. And we all know that the sum of the angles of a triangle in Euclidean space is 180 degrees. In Euclidean space, any circle you draw satisfies that requirement of circumference to diameter. So in other words, any circle has, if you do a measurement, it will give you a result that is exactly in agreement with the value of pi. And today, pi is known to more than 10 to the 12 decimal places. And there are some individuals in the world, there's one person in China who knows the digits of pi to 40,000 decimal places. An extraordinary thing to do. So pi is universal in Euclidean space. But if space is different from Euclidean space, then the experimental value will differ from the calculated value. Well, let's just look at this in history. And it's interesting that it crosses all cultures. One of the world records was made by this man, Zhu Zhongjie, in China, 480 AD. He determined the value of pi to be equal to this number, 355 over 113, or 3.1415929, nearly the right number, just a small error, 8 times 10 to the minus 8. And that record held for a long time. Others were still making similar parallel calculations at the time. But in the Arabian world, or the Muslim world, Jamshid al-Kashi in 1400 AD computed pi to 17 decimal places. Got this value for pi, enough to easily compare it with the modern experimental values. Well, all of that is just a little bit of the way that our culture has focused on Euclidean geometry. The first person to question anything about Euclidean geometry was Carl Gauss, who's famous in electromagnetism, but is not so famous for questions about space. But he said, why should we believe this 2,300-year-old geometry of Euclid? He was the first person to question whether that geometry was a valid description of the universe. And he built a beautiful instrument to try to test it. He published a theorem which says the shape of space can be determined by measuring angles and distances. Here in Frascati is the Nautilus gravitational wave detector that was trying to measure ripples and is still operating. I saw it just an hour ago. That is trying to measure changes in the shape of space, which are gravitational waves, by measuring distances, by measuring the length of a metal bar. And the Virgo detector is doing exactly the same thing by measuring distances between distant mirrors and using lasers to measure those distances. So Gauss had it all worked out. He built this instrument and he did this experiment with the instrument. He had 3 people. This is a telescope combined with a mirror to reflect sunlight. And what he tried to do was to measure the sum of the angles of a triangle between 3 mountains in Bavaria. If he had been right in his questioning and sufficiently precise in his experiment, he would have found that the sum of the angles was not 180 degrees. But at that stage, it was just a question. In fact, his precision wasn't good enough, and he didn't observe anything. But his student was Riemann, who developed the mathematics of curved space geometry and laid the mathematical foundation for Einstein to come up with his theory of general relativity. And his theory, and all of this Einsteinian revolution, involves thinking about space and time as a unified structure, space-time, that space-time is elastic, it has energy, it is not just a sort of conceptual framework, but it is something real that contains energy. The shape of space-time is determined by matter. He also showed that light comes as streams of photons. And he showed that falling objects follow their shortest path in space-time. So that's just a summary. And as most of you know, it was very soon after he published his theory that the deflection of starlight past the sun was observed. And this is the famous story from the New York Times, front page, 1919, where the deflection of stars near the sun was first observed as the first observation, experimental observation, that the space around the sun was curved. What's interesting here is that, first of all, this would imply that the experimental value of pi near the sun is wrong at the 6th significant figure. So that number that you calculate is different from the real number that would apply experimentally in the universe at the 6th significant figure. But there's something else in this story which is very interesting. And this relates to the main topic of my talk today, which is why we haven't taught any of this to our young people in schools, why it is not part of the school science curriculum. And it's this statement that was put in the bottom of this front page headline. "No more in all the world could comprehend it," said Einstein. He was already saying that this is too complicated for anybody to understand. I am a genius. I can understand it. Other people cannot. And that story was perpetuated. Some of you might have heard the story of Sir Arthur Eddington, soon after he made the measurements of the deflection of starlight. And the journalist said to Sir Arthur, "Is it true that only 3 people in the world understand Einstein's theory?" And Eddington's reply, some of you might know it, was this: "Who is the third?" So there was this idea that this was elite knowledge for just a few people. And another person, one of the brilliant physicists of the 20th century, Richard Feynman, had words to say about the people who inherited Einstein's theory, who worked on Einstein's theory, developing the mathematics, trying to understand it in detail. And he said People who work in gravitational theory believe that the equations are more difficult than in any other field, and from my viewpoint, this is false. If you look at the equations used by physicists who study the mechanics of Newtonian mechanics of orbits or of strains in structures, you can find just as complex mathematics. You can make Newtonian physics as mathematically complicated as you want. And Einsteinian physics is the same. But you can also simplify both of them. And that's what's important here. Well, one of the great heroes of this field is John Wheeler. He had a really good way of finding nice words to describe some of the physics that comes out of Einstein's theory. He is the person who invented the word black hole in 1967. He captured the essence of Einsteinian physics. Today, astronomers believe that in our galaxy there are 20,000 black holes swarming around the central black hole, which has got a mass of about 4 million solar masses. And so our galaxy has got Einsteinian physics right at its core. It's part of the universe as we see it today. If this is going to work. So we see things, this is a simulation, but we see things very much like this in the universe with the Hubble Space Telescope and things like that. This is a black hole, a simulation of a black hole passing across the Andromeda galaxy. But other images, like one I'll show you in a moment, is something that you can just, is a photograph from the Hubble Space Telescope that for one click on Google, you can find that image. It's accessible to all of us, real images of this type of thing. The other thing that Wheeler did was to introduce a way of expressing Einstein's theory of relativity in a very simple phrase that I think all children could learn and could understand at a very early age. Matter tells space how to curve, space tells matter how to move. And out of that comes the idea that gravity is not a force emanating out of planets, some sort of force coming out of the ground, but it is the force you have to apply to stop things from following a gradient in time. Now that's a strange idea, but it's not so strange when you relate it to real experiments that are done with clocks, for example. And of course comes out of Einstein's theory, the idea that if space is elastic, it can sustain waves, and so there will be waves passing through us, through everything, and those waves change the shape of everything. So the shapes of objects are being changed by gravitational waves. This gives us the new way of exploring the universe. It gives us new technologies, which some of us here are working on. What we are doing is inventing gravity radios that can allow us to listen to black holes, to experience some of this Einsteinian universe that can be otherwise rather difficult to observe. In 1993, the Nobel Prize was given for the proof of existence of gravitational waves because a pair of neutron stars was seen to be spiraling together closer and closer, getting faster and faster according to this curve. And the theory in the experiment agrees perfectly, and that tells us that gravitational waves exist, that energy is being lost by systems like that. a picture of the sort of system that Hulse and Taylor discovered. The two stars spiraling together, and you can see space in the background rippling with gravitational waves. And I thought there was one more here. Anyway, so the next vivid demonstration of the reality of these ideas is the one from NASA's spacecraft that was called Gravity Probe B. Gravity Probe B measured the shape of space around the Earth, observed that its shape was rather like this. The experiment can be interpreted as a measurement of the ratio of the circumference of the orbit of this spacecraft compared with the diameter of the orbit. And the discrepancy here is 28 millimeters. So if you use the Euclidean formula for the perimeter of a circle, circumference of a circle, you will find that for this circle, it is wrong at the level of 28 millimeters. Now, it's not a lot wrong, but it is wrong. And it means that the formula that if you were a teacher, were teaching at school, it would be most important that you could say this is an approximation. It does not fully describe space. And here are these another one of these gravitational wave detectors, as I said, searching for these ripples in space. So let's now just have a look at what we teach in schools today and compare it with the real world. In school, we teach Euclidean geometry, but as I've emphasised, the geometry of the real world is curved space geometry. We teach that space and time are absolute. Maybe not by saying it is absolute, but by implying that space and time are absolute. And in reality, space and time are relative, and they're unified into space-time. We teach that light is a wave and that electrons are particles, but in reality, we have a wave-particle duality. We teach that energy is massless, when in reality E equals mc squared. We teach a sort of Newtonian determinism, when in reality there's quantum uncertainty. And we teach that gravity is a mysterious force, described by Newton, but it is always made out to be mysterious, whereas in reality, gravity is a simple manifestation of curved space-time. So, my question is it necessary to teach students all the old science before we teach them the truth? The next question, can we increase the motivation and interest in science by teaching modern ideas up front instead of postponing it to some future time when they have learnt all the old stuff? And is it too difficult? Now, most people will probably agree with this, and they'll agree with this, but mostly they'll say, oh, but it's too difficult. We can't do it. It's too hard. So the most important point of my talk is to try to show you that it is not too hard, that it can easily be done. I told you that curved space is one click away on Google. Here is, if you put in gravitational lensing into Google Images, then this is one of the first images you will find. And this is an image of a galaxy completely distorted by the gravitational effects of a foreground galaxy. This galaxy is has been distorted into a ring. Its real shape is not like that at all. So, so we keep the beautiful ideas for an academic elite. We don't bring them to the ordinary people. And I believe that the fact that we do that is linked to the plummeting enrolments in science, the loss of interest in science. Why are we doing it? And the answer is that teachers have not been taught the truth, and the reason for that is that people think it's too difficult. And I think that all students get the feel that they're being taught old science instead of learning the new science. The main problem is that we teach Euclidean geometry as if it was an exact description of the world. We, of course, have to teach that this is a very useful approximation, but it is not an exact description. It is a beautiful and elegant invention, but it's an invention of the mind. So those are what my concerns are. Well, I've given many, many public lectures about gravitational waves. And every time I've given a public lecture over 30 years, always trying to find better and simpler ways of explaining things, I have somebody coming up to me saying, "Wow, you must be a genius to understand that. It's all so complicated. I'm so confused." And some time ago, I was doing a special program for gifted students, for very talented students from the top schools in Australia. And they had all come to our centre, and this was their first exposure to the ideas of general relativity. But I took my 11-year-old son with me. He was 11 at the time. And on the way, I started telling him, I asked him if he would be my assistant because I wanted to do some demonstrations and things. And he started asking me questions, and I realised that he could understand some of the things that I was talking about. And he's not a particularly gifted student or anything. He probably really thinks these ideas are a bit boring. But he showed me that he could understand it. And I said, "Would you like me to come into your classroom and I'll tell all the class about these things?" And so that was the first chance where I had the opportunity to see if it was possible to teach to very young children some of those ideas. And I then went into the school with 11-year-olds, and we tested the children with questionnaires and things before and afterwards to find out what their understandings were. But we also asked them questions like, "Do you think you are too young to understand these things?" And universally they said, "We're not too young to understand." And then I started to understand what is actually happening with these young people. They had completely open minds. They were not astonished by any of it. It was just new and interesting things, but they were not astonished. And the reason that people are astonished by it is because it's contradicting their preconceived views. I think that young people at that age are still learning the language of reality, just like they're learning their own language and maybe learning, like so many Italians, becoming very good at foreign languages. They are learning the language of reality. We all learn a language of reality, a language to describe the universe. And as Einstein said, common sense is the collection of prejudices acquired by age 18. So we create a set of prejudices about Euclidean geometry with young people, and then after that, at the age of 20 or something, when they come to university, we start to teach them what is our more modern idea. So if an idea can capture a child for a lifetime, what's clear is that the Euclidean idea has captured the world for millennia. And Aristotle's doctrine of free fall captured the Western world for something like 2,000 years until it was overthrown by Galileo. So those are examples of people having these preconceived views and being captured by those ideas. So if we're going to make the language of space and time, the language that we know is the best description of the universe available as part of our culture, we've got to tell it to children when they are young, when they're forming their common sense view of the world. So that is what we are arguing. The one part of Einstein's physics that most people, if you ask somebody in the street, what do you know about Einstein's physics? Some people would say E equals mc squared. Many people wouldn't really know what E equals mc squared means, but they will have at least heard of it. But they don't know that E equals mc squared means, for example, that the sun gives out 4 million tonnes of energy every second, that each of us uses about 1 milligram of energy in a year, that your mobile phone is a little bit heavier when it's fully charged. Those ideas we tested with young people, and again, for them, it seems quite easy and straightforward. It's not something surprising. So our science education enrichment project was trying to find out experimentally with classes of different ages what was the appropriate way to change the curriculum. What we did was develop curriculum material, develop all sorts of classroom activity-based learning. I want to show you some examples of it in a second. We've also run professional development programs for teachers to try to upgrade the knowledge of teachers to the point that they could feel confident to teach young people the Einsteinian physics. And we're developing a teacher's handbook and video material, and that's still progressing. In asking the children about the work that we've been doing, as I already said, they say they're not too young to understand, and when we've tested them, they've shown excellent performance in their conceptual understanding. We've tested with 16-year-olds, and they say it would have been good to have learnt these ideas earlier. 95% of the students we've asked reject the necessity of learning Newtonian physics before they learn the Einsteinian ideas. And one of the most interesting things that we discovered was at the end of programs that we've done, we've asked what was the most interesting thing that you learnt and what was the most difficult thing that you learnt. And we found a very strong correlation between the things they found most interesting with the things they found most difficult. That says that children want to be challenged. You don't want to always be making everything much easier. You want to be challenging them. And the sort of ideas that they chose specifically as the ones they found most interesting was the idea that gravity is an effect of warp time, the principle of maximal aging that says that everything ages at the fastest possible rate unless you apply a force to it, which is a direct outcome of general relativity, and the idea of single photon interference, that how is it that you can have interference happening when there's only one photon present, which is one of the central parts of quantum mechanics. With the teachers, what we've tried to do is to find out how difficult it is for them to learn because many of the teachers that we have been working with are teachers who have been not trained in physics at all. Some of them might have been sports teachers who were asked to teach physics. Sometimes they're primary school teachers who have no special training in physics at all. And we want to find out how difficult it was for them. And we want to get also to get their advice as to how we should get this into the curriculum. The hardest thing of all is to change the national curriculum, because the inertia involved in that process is terrible. And I have to say, we haven't solved that problem yet. But when we did testing, 35% of the teachers scored less than 50% in a pre-test designed to find out what they knew. Mean score about 52%. After a one-day intensive program, 70%, 95% of them scored more than 70%, and the mean score was 81. We could see that in the testing, the teachers could really improve and develop a level of confidence. Sort of questions that we were asking were questions like this. What is gravity? What is light? In geometry, can parallel lines ever meet? Here's an interesting answer given in a pre-test. Light is responsible for the visibility of things. Light removes darkness. You can find statements of that sort in Euclid's book Optica, published 2,300 years ago. In post-test, they know that light is an electromagnetic radiation with wave and particle properties. And the teachers all agree that it's feasible to do this. Of course, I have to say that the teachers we have, that we have tested, have to some extent been self-selected. So you have to be a little bit skeptical about the numbers that we have here, because this is just the groups that we've been able to access, and that doesn't necessarily represent all teachers. But we found that the teachers are very positive about it, happy to introduce the programs, but they also realise that it is important that they get some training. So how is it we've done this? How have we made it work? And probably a lot of you will be most interested in what are the methods we've used to get these ideas across. And the most important one, I think, is the use of analogies. How do you get the idea of a photon across? Well, we've got some really nice analogies that we've used. We wanted to get the idea that photons start from the idea of particles, not waves. And so what we've used is a very popular children's toy called a Nerf gun. A Nerf gun is a brightly coloured, I'll show you a photo in a moment, a brightly coloured machine that sends out foam bullets. And you can get electric ones that will fire maybe a bullet every second, and so you have a stream of bullets like the photons coming out of a laser. And so we've done many experiments with those. Geometry in curved space. You need a practical way to do geometry in curved space. You have to get away from the flat piece of paper. What is a suitable flat piece of paper? Suitable space to use? Well, we have used the Chinese cooking pots called woks. And I'll show you some photos of that. We'd used lasers and have a very beautiful experiment that I'll show you a little video of, where you use the lasers to look at reflection interference from soap films. Works extremely well, also diffraction. But then we do a lot of thought experiments. We also make use of lots of YouTube videos, and some things are not easy to do experimentally. For example, single photon interference. You can't do it very easily experimentally, but there is a beautiful video available on YouTube that shows single photons interfering and images breaking up. Ocean waves from Google Earth, and there's so many resources out there. So here's some experimental curved space geometry. These are little magnets, and here our students are making triangles on a surface of a wok. The little magnets from magnetic assembly toys allow you to survey accurate straight lines. You can be sure that they are the shortest ones by using a piece of string, and then you can measure the circumference of the triangle by measuring the total length of string, and you can measure the angles and find out how the geometry works in this curved space environment. And this is very cheap to do, very, very simple, and students come up with graphs like this that show that the sum of the angles of a triangle, if they're very small, they tend to converge towards 180 degrees, and as the triangles get bigger and bigger and bigger, the sum of the angles gets larger and larger. The idea of space-time. I haven't really got time to talk about all of it because it is something that needs to be developed quite carefully. But we always make use of this sign, which says McDonald's, 25 minutes away. Does that mean if I stand here for 25 minutes, McDonald's will arrive? I saw one in Rome, actually. It said McDonald's uno minuta. And of course, what it says is that something about velocity is connecting space and time. And at some velocity, in 25 minutes, you'll get there. Seeing this one is from America, it probably means 80 miles per hour or some speed like that. But clearly there is a speed that connects space with time. And then, of course, you can say, well, what is the speed that we should connect space with time? But to precede all of that, it's important to ask, how do we measure space and how do we measure time? And to show people that we measure space by some completely arbitrary units based on some bar of platinum in Paris, and we measure time by some equally arbitrary method that probably in history goes back to the pulse of our heart, something that gave us roughly 1 second. And then you can say, well, if you're going to have a universal connection, there has to be a velocity to make the connection, and of course that velocity is the speed of light. Students work that out for themselves, and then they can make space-time diagrams. And we ask students to do space-time diagrams of their journey to school, and that one can take you very well towards understanding many things, sophisticated things, such as this one. Well, adding this thing that we call Einstein's first law of motion. Einstein's first law of motion is analogous to Newton's first law of motion, but Einstein's law says that all freely falling objects follow the shortest path in space-time, and that's the one that leads to the principle of maximal aging, that you get old fastest in free fall. I was quite astonished that bright 14-year-olds were able to actually calculate the time difference between the top and the bottom of a tower based on those ideas. So I would say that wouldn't be quite general that all students, but in a talented class of students, students were able to calculate the time difference, which is 10 to the minus 16 per metre. It's g over c squared per metre is the time difference as a function of height that comes from general relativity. And that, of course, is the origin of gravity. Now, I want to show, I did something slightly wrong with this, but I want to show you a video that was made by one of my, oops, I've gone wrong. Oh, where am I up to? Was one of my PhD students made the video of something we were doing in a class where we were using, Nerf guns to take photographs and also to show the uncertainty principle. This is not a very professional video. There you go. So that's all probably a bit confusing to you, but what we do is have some of these guns shining lots of photons at the person, and the bullets stick to a whiteboard. And so in the end, the person goes away and there's a silhouette photograph left of the student. So our analogy here is these Nerf gun bullets are photons, and here we have some photographic medium which is, has allowed an image to be seen. But now I want to show one extra little bit, if I can. What's happened? There we are. Just want to play it through. I want to show you the uncertainty principle here. This is now measuring a balloon. What we've been learning is called quantum. There. So there you saw two things, which was photography with Nerf gun photons, and then measuring a balloon with Nerf gun photons. And the balloon, because of its low mass, recoils very badly, and so you get the quantum uncertainty principle obviously happening. You can't tell the precise position, and the more photons you use, the greater the recoil. And so I think they get that idea. Now the next is teaching them about matter tells space how to curve, space tells matter how to move. The space we use is this material which we call lycra. In America, they call it spandex. What do you call it in Europe? Lycra. Okay. So this is a standard sheet of lycra. And then we do some...
We'll actually head in a dead straight line, as you can see there.
Empty space.
It's forced to follow that curvature and it'll go around that object. That's known as an orbit. In this case, a decaying orbit, the ball can't maintain its speed, so eventually it will succumb to the gravity it feels and be pulled in. It's actually...
Here is the Earth-Moon system.
And then the slingshot back again. That's it, so it's the figure 8 there. Yeah.
So that demonstrates very nicely the idea of space tells matter, matter tells space how to curve, space tells matter how to move. Of course, it's very important to explain this as an analogy, but that's a very simple demonstration to set up. It costs, €5 for the piece of lycra, stretch it over a wooden frame, and then collect some golf balls, and it works very well. And back to the Nerf gun, this is just a photo to show the photoelectric effect. In this case, we have ping pong balls inside saucers. And here is the Nerf gun shooting bullets at these electrons, which are confined in potential wells. And you can change the size of the potential well, you can change the size of the balls, and see the balls being released from that system, so illustrating that idea. Now, the last one is to show interference, and one of the most important ideas here is to teach people about the distance between photons. And I'm sure that a lot of you will never have thought about this. If you consider looking at a 6th magnitude star, that is the dimmest star you can see with the human eye. The number of photons per second entering your eye is about 300 per second. So with the Nerf guns, we first of all ask the children to say, how far apart are the bullets, the Nerf gun bullets coming out of that gun? Or you estimate the velocity, and or you can ask a question like, if I have a machine gun firing a bullet at 1 kilometre per second, and I fire 20 bullets per second, how far apart are those bullets? And people can see easily, they are 50 metres apart. So then, I have 300 photons per second coming into my eye. How far apart are those photons? Well, they're travelling 300,000 kilometres per second. So those photons are 1,000 kilometres apart. When one photon enters my eye, the next nearest photon is 1,000 kilometres away. And then say, suppose you just screw up your eyes a little bit and look through your eyelashes and see some diffraction taking place. Then you are still looking at the 6th magnitude star. It now has changed its shape a little bit because of the diffraction pattern, but when one photon is passing through there, the next photon is 1,000 kilometres away. Clearly, this is not interference of the photons themselves because they are so far separated. So then you can say, well, what is an experiment you can do like that? Well, you want to have an experiment where the size of the interference region is very small. And appropriate choice is a film of soap, a soap film. So we make, and this is a very simple thing. I told somebody about it told Carlo Bradascia about this at Virgo last week, and he said, oh, that sounds really good. Can we try and make one? And within 5 minutes, we had found a piece of wire. We'd gone to the kitchen to get some soap. No, we went to the toilet, actually, to find some soap. We made some soap solution, and we did this experiment, and I'm going to show this to you just here in this next slide. The most important thing here is that you make a soap film and then you don't look at the light which passes through the film, you look at the light that reflects from the film. And that will show interference between the two paths of light from the front and the back surface of the film, which is about 1 micron thick. And if my video will work, you can see this as a live video. So that is a draining soap film through a little loop of wire. And you can see all sorts of beautiful physics that goes on inside the soap films. And in a little while, the film breaks. But you can see, and if anybody wants to know exactly how to make one of these, I can tell you afterwards, so I have to show you with my hands. So that allows you to demonstrate this sort of quantum world. And so you can also say, in this situation, when you're doing this interference experiment. You have interference between a photon and if you want to think in terms of another photon, the other photon hasn't yet been created inside the laser, because in this very thin film, again, the probability of there being two photons at the same time is rather small, depending on the intensity. So, I think that these are all ideas that everyone can know. They're not ideas that have to be left for either the mathematically talented or for the scientific elite. These are ideas that should be for everybody. That we live in curved space with rippling geometry, warping time. The world is quantum. Quantum reality underpins technology. Matter has wave behavior, and waves have particle behavior. But it's really important that we still stress that the old approximations are still useful. And clearly, if you're a builder building a house, it doesn't really matter if the Earth is round or if the Earth is flat. So the flat Earth is still useful if you're building a building, but it doesn't mean to say it is right. The truth is important. Euclidean geometry is still useful for architects. Wave properties are useful for radio engineers. Galilean relativity is okay for a car crash, but it doesn't mean to say it's the truth, and we need to separate between the truth and the things that the useful approximations. So the bottom line is that the modern world depends on Einsteinian physics. And what I like to say to the children is it's all in your mobile phone. Everything in your mobile phone is Einsteinian physics. The GPS navigator is corrected for the time difference between the satellites and the Earth. And the semiconductor physics depends on electrons having wave-like properties. Our experience is that the children say it's fun and it's interesting and they're not too young to understand it. But for the second last slide, what Einstein said is education is what remains after one has forgotten everything one learnt at school. Now, I think that's a very cynical attitude and a sad attitude, but it's also true. And we need to try to fight that and stop that from being true. So we need to learn how to teach children the truth. And the last is a referee's comment. And an anonymous referee, I don't know who the referee was, but he said this was for a funding application, and he said, an approach that directly teaches students our richest, most current and most productive ways of understanding the universe just makes sense. It's certainly also an innovative approach. It's an approach that has that's not been attempted anywhere in the world to date. The findings have potential to be revolutionary. Well, I'm not sure if it's revolutionary, but I think it's something that we can all try to do. Thanks.
So, David, thank you so much for this beautiful seminar. Questions from the audience?
Let me be a little bit, let's say, skeptical somehow. I mean, I appreciated very much your approach. However, what I want to ask you is the following. Basically, teaching basic geometry, Euclidean geometry and basic science is something which is can be relevant for everyday's life application. For instance, if you want to know how well you can fit your new furniture in your house, you do not need Riemannian geometry. No, you just need. So, in principle, how would you somehow combine the need for the usage of simple mathematics for everyday life with these new ideas, which by far are somehow a kind of a little bit more complex.
Yeah. Well, I agree that it's important that people know that everybody should learn that area of a rectangle equals length times breadth. That's what an engineer needs to know, it's what an architect needs to know, things of that sort. But at the same time, your argument could be used to say we shouldn't teach anybody that the Earth is round because flat is good enough for building roads and doing all the things we do. But my claim is that the truth is important and that people need to know the truth and they need to know the tools for living. And the tools for living involve Euclidean geometry. And so I don't deny it's important to learn Euclidean geometry, but we should never tell the students that that is exact. We need to tell them that that is an approximation, that the reality is this, but you can use this when necessary. We already do it for we know the Earth is spherical, but we don't use spherical geometry when we lay out building lots. So it's just a matter of adding the truth without subtracting the useful methods.
Oh, hello. I think this is a very stimulating activity and potentially attracting young people towards science since they are very young. What I wanted to ask you, are actually three things.
Yeah.
The first is, which was the background of the teachers which were trained by you?
Yeah.
The second, if you told them that there is actually a tension between quantum mechanics and gravity,
yes,
in spite of the success.
Yeah.
And the third is, actually a statement. I don't really agree with that statement of yours about the interference between photons coming far away. Okay, but that's another story.
Okay, well, so one relates to interpretation, the last one relates to interpretation of quantum mechanics, but your first, what was the teacher? Oh yes, so there, as I tried to emphasise, the teachers were to some extent self-selected, but they were different, but they came from different backgrounds. And we found that the professional, experienced teachers who had been teaching, say, years 11 and 12, the last final years of high school, tended to know some of the modern physics. But the younger students, the younger teachers, some of them were primary school teachers. They had had a general training in education where they will have had some lectures in science. They knew none of that. So we had this range of teachers where there were primary school teachers with, I'd say, low-level training, middle school teachers who were generally trained in something like sports science, and they were still teaching biology and physics and chemistry, and then there were some of the others. I'd say it is not a complete survey. Only the teachers were able to access, because it's not so easy to access large numbers of teachers. So your second question?
And the third was whether you teach them something about the tension between quantum...
Oh yes, yeah. And I do think that's really important. I think the worst thing we can do is to teach students that we know everything and it's all complete. That what is inspiring for people to go into science is for there to be mysteries. So all of the mysteries of the universe are really important to emphasise. I didn't emphasise it in that in my talk, but that is really important. That we need students to realise that we don't know everything about the universe by any means, and also the fact that the interpretation of quantum mechanics is something that we can't understand. I am actually slightly worried that some of the students might be put off by the difficulty to understand quantum mechanics. But that doesn't mean we shouldn't teach it to them. Yeah.
First question, the youngest people in your videos was about 11 years old probably.
Yeah.
Did you try with the younger, I don't know, 6, 7, 8 years old? Because there is some age in which the magic part, the monster, the cartoons had to translate in some more scientific. So, which is your experience with younger people?
No, well, my experience is really only with probably 11. I've done the things with other classes, but not trying to teach these things. There is another group in Australia that is trying to teach atomic physics to younger children. And it seems to me a perfectly appropriate thing to be doing, but we just haven't focused on that. What has happened is we've generally had a PhD student who's chosen a certain range of children to work with. We've had one that's working with what we call year 9. This means just counting the number of years since they started school. So year 9, year 10, year 6, year 7. Those are the years we've worked with.
And the second question, you mentioned that you did this experiment, this lesson with a selection of very good students. Did you try also on normal classes? So
most of what we've done has been with quite normal classes. Okay. Only with the 16-year-olds did we do it with selected very bright ones.
It works with normal...
yeah, it does. And we've done it with one group that is even... it is probably a school from a deprived area of Perth. And that seems to have worked quite well there. We've used slightly different techniques. Another technique we've been using, which I didn't mention at all, is drama. And we have two beautiful little plays, one about quantum mechanics and one about gravity. And I think they work really well with the kids as well. And where children, there's a place for all everybody in the class to have a role in a play, and somebody will be playing Newton, somebody will be playing Einstein. Many different characters from history come together to argue the truth.
Hi, David. Did you make any long-term impact of your program on the student?
No, we haven't been doing it for long enough. We are hoping that this year we will be measuring the effects of our program on students that we tested last year. And those were 14-year-old students, and we'll be testing them when they're 15. But real long-term effects, we don't know. We haven't been doing it for long enough. And it can be difficult.
And David, how many students could you test?
We did it with 6 classes. At one school, we had 6 classes in parallel, and the PhD student was working a whole week over a period of about 10 weeks with the students. And another PhD student has been did a total of about 20 classes for one class, I think it was, so about 30 students. I can't remember if it was 1 or 2 classes. Did Jyoti do 1 or 2 classes? Maybe 30 or 60 students, and then others have been about 30 to 60 students. So that's the typical class size.
I have
a comment more than a question. So the main message I got from your presentation is probably that the right approach in teaching science is to set that science is not an exact picture of reality, but it is an approach. And so you use the best approach depending on the scale you are studying. So if you are dealing with car crashes, you use Newtonian and Galilean relativity or equation. When you deal with stars and particles, you have to include relativity. So this is the message, the right message to give to children or not?
Well, what I would say is that we are trying to have the foundation to be our best understanding of the universe. We have to make it clear that we don't have a perfect understanding, but we at least give the best understanding. We do want people to learn that there has been, that our understanding has been getting better and better over the centuries. And, but I think I would argue very strongly that the understanding we have today is much better than the understanding we had 100 years ago, which is better than the understanding we had 200 years ago. It is a process of progress. So we want to be starting by introducing ideas from the very top of our understanding of the truth, but then reminding students, reminding everybody that we have approximations that we always make in our lives and need to be able to make those approximations to be able to do simple things.
Yeah, also because it's not worth to use relativistic correction when you are dealing with car crashes, because they don't have nothing. So I think this is also an important message you have to pass to the children. So that you how to say, you introduce something more precise when you need it.
Yeah, but that contrasts with the way that we teach at the moment, where we say that we make the students, we've picked a point in time which is probably about 1850, and we say we teach you everything that we knew about the universe up to 1850, and then at a later stage in your career you can learn some new things. And that, I think, is the big mistake that we are making.
This I agree completely that some fundamental concept of modern science, let's say, should be given at the very beginning of your training, so that you are not, how to say, worried when you are introduced to them. But probably is also important to remark that for everyday life you can survive also without knowing the details of quantum gravity and relativity or things like this. Thank you.
Yeah, I agree.
Good evening. I'm talking for a teacher who is not here because of the age, but this teacher for 20 years tried in his classes from the first one in secondary school to the fifth one, this approach very similar to yours.
Really?
Yes, in north of Italy, and I know him by email because I've been chatting with him about this approach, which is really interesting to me. I find it, well, I wanted to say that because there is an example. There is a person who did that for 20 years successfully, so in Italy. So it can work. I just wanted to tell you. Yeah. And yes, for example,
could I just ask if anything has been written or published about that?
Sure. Yes, I know. There is a website of this gentleman. The name is Rodolfo Damiani, and he has, of course, all the syllabus and courses, and he developed. And as far as I understood, the first year is all about what you said, just to introduce this new way of knowing the reality, and then building up in the next 4 years, or the rest. I don't know the details yet, but of course, contacting him he will be very happy to share. Of course, he's retired now. I think he retired a few years ago. But and he did it in the secondary school with a scientific, a specific scientific curriculum from Italy, PNA, you know and so it is possible. Yes. And thank you very much for your conference.
I should just say that we've been doing a survey of the curricula in different countries to try to find out, you know, what, and they're generally fairly similar. One of the countries that has got the most developed curriculum in that area is Nigeria, surprisingly. But also some experiments were done in Lebanon in the 1980s with this type of teaching, but there's rather little about it. I don't know if any of you have ever seen some little videos that you can get on YouTube that are called Minute Physics. There's a very nice one which has basically all of what I was trying to say, all in 2 minutes, and it's called Dear President Obama. I don't know if anyone has seen it, but in this, if you look up in YouTube, Dear President Obama, you see this beautiful little video that is saying why they should modernize the physics education curriculum.
Excuse me, it works. There is something I don't agree with your speech, not the approach, the speech. The reference to truth. Yeah. I don't think truth, generally speaking, and in particular about teaching. I'm very close to some of the question and of the colleagues that preceded me before. And what I want to say is that you can provoke some new thinking in students, starting from ordinary things they live today with new technologies and problems. You can insert some of these ideas in the traditional curriculum. You can provoke them, you can present to them different and new things, but I don't think that you have to modify in a very structural sense what we do at school, because it's so revolutionary, I think in a didactic sense, inertial, the first law of mechanics, the ideas of Galileo are so revolutionary for them in modifying their brain, their mind, and you can continue starting from there to provoke them and present to them different approaches, different problems, different way to observe reality and the world around them. I don't know if I was clear in my speech, but I tried to not to present any truth. We don't have truth. We try to understand what is around us.
Well, I would say that there is that we don't have any absolute truth, but we have the best approximation to the truth. It's a better approximation to the truth that the Earth is a sphere than it is that the Earth is flat, for example. So, but yeah, you mentioned Galileo. What I always have found very interesting is that that we should think so intuitively today in terms of Galilean relativity, because before Galileo, that was quite a revolutionary idea. I always found it really astonishing that people should have believed Aristotle's views of free fall when you only had to take two objects and drop them on your feet, and to see that the heavy one doesn't get there first before the light one, even though that was clearly espoused by by Aristotle. So there are truths there are things that we can say are definitely untrue, and I think we can say that definitely the nature of space around us is space which is curved and not space which is flat. And in particular, gravity is explained completely naturally in terms of the ideas of the warping of time, but is not simply explained by Newtonian physics. In Newtonian physics, gravity is simply some mysterious force that comes out of objects. And you find many, many cases where people and teachers will say that gravity is a mysterious force and nobody understands it. And that does not represent the state of our general understanding of the universe. So I don't quite agree with you, but I don't want you to think that I'm saying that we have the absolute truth. I'm not saying that. The Catholic Church may say that, but I'm saying that it is the best approximation to the truth.
It depends on the problem we have, the best approximation.
Huh.
Okay, there is one more question.
Mm-hmm.
Okay.
I wanted to ask you if you've considered that some teachers are not, I could say not so young, so they have not lived a period of the time where they could study a particular matter, for example, modern physics. Mm. So could be this fact the cause of the problem you mentioned?
Well, I think that what we are doing is bringing the ideas to a level that are sufficiently simple by using the analogies that we are using and using the sort of resources that I showed in the videos. It doesn't become particularly challenging for a teacher, an older teacher who has been trained in other ways, except for the fact that they do need to change their curriculum material. But I think and from our testing of teachers, there have been quite senior teachers amongst the ones we've tested. They do seem to be able to accommodate the ideas quite easily. Mm-hmm. So we don't know enough to be able to say anything definitive, but I believe it's quite possible.
Okay. Mm-hmm. Thanks.
Okay. There's some coffee outside, so if there's no question, comments, we can go on outside. And let's thank again a lot the speaker. Thanks so much, David.
Yeah.